Okay, so here we have a wave optics interference question where we're dealing with microwave radiation going through a double slit and then figuring out the intensity pattern uh, on a screen 2.5 meters away. So the first part is just a straightforward calculation before we actually get even to any of the interference stuff. So we're given the wavelength and we're asked the frequency. And since we're told it's microwaves, we also know the speed. So we wavelength and frequency and speed are all related with that. We can rearrange, and we should also note that the speed is the speed of light. So you plug that in, and that's our frequency. So that's part A. Just making sure you remember that relationship and remember that the speed is the speed of light. So in part B, we need to just do a sketch. We don't need to do a calculation per se, although we kind of do because we have to be precise. We have actual number labels of distances, so we need to figure out where the maxima and minima will happen. So we can't just make the shape general. We have to be a little more accurate about where the maxima actually happened, but we don't know how much intensity there is, so we don't have to worry about the vertical axis value. So we know that the biggest maximum, the central maximum, is at the center, x equals 0, so that has to be a maximum. And our job is to figure out where's the next maximum, and then if that one is in that plus or minus 3 meter range, we have to calculate the second maximum and so on. And we remember from the equation sheet we have d sine theta equals m lambda. And this one is going to find the maxima of a double slit. And we are also going to use the small angle approximation and say that sine theta is about equal to theta. Right? And so if I redraw that screen, right, what we're talking about here is we have that, and that, and that. And one is that path length difference I'm going to color over in blue. Right, that's what we really care about. And if the angle is small, that is something we can solve for pretty straightforwardly. And that's where that d sine theta comes from, but we have to remember what sine theta is on this picture. Right, sine theta is really from this triangle. So that can be rewritten as, right, this is L and that's D, so that's about equal to D over L. Oops, sorry, that's wrong. Yeah, so I was missed one label in here. So it's not that triangle that we care about, it's the one formed by where it intersects. It's over here. This is the location of that maximum point, and then this is L. So sine theta is approximately going to be x max over L. Right? And so now we can put all this together to solve for where the next maximum happens, which is at m equals 1. Okay, so d x max over L equals the wavelength, right? That'll find us the first maximum, and we rearrange and solve like so. And when you have all these numbers, so we can plug them in. And if you do so carefully, you get this happens at 0.30 meters. And since we know it's symmetric, we can write this as plus or minus, right? It has to happen at both. And since our graph only goes to that range, we know we only have to draw up to that maximum. We don't need to calculate where the second maximum would happen at, or so on. So now we can have our graph with that knowledge and some other facts. So I'll go with that. Okay, so we calculated that it is the maximum at the center, we know that, And the next maximum happens at plus or minus 0.3, and it should be a little bit lower. Right? Each maximum is a little bit dimmer. That's a little off. And it's symmetric, so I should make the maxima the same height. And then the other thing we know is that the minima are roughly in the middle of the maxima. So if our maxima are at 0 and 0.3, our minima are going to be around 1.5. And now we just need to remember that this is kind of that sort of sine curve type shape. And so we just kind of connect these points together. It has to look kind of like that. Right, roughly speaking. Okay, and that's really about all it is. It doesn't have to be drawn perfectly, but it has to be curved, clearly, not straight lines. And you have to have the minima and the maxima roughly the right spots. That's part B. Part C, we're now going to figure out the highest and lowest intensity of 3 different locations. And really this is just making sure, in sort of a secondary question, that we've carefully considered the relative peaks. So we have 3 positions at 0 meters, and that's right here, at 1.5 or 0.15 meters and 0.3 meters. Right? So the biggest key is that you have to recognize that around 0.15 meters is the minima, so that's the least. And we know the central maximum is always the single brightest spot, so that has to be the most. And then in terms of explanations, right, we already calculated why the 0.3 point is a maximum, right? That's a constructive interference statement. If you wanted to show that the 0.15 point is a minimum, you'd have to do d sine theta equals 0, yeah, I was right, 1 plus 1/2 lambda, right? This extra half wavelength for destructive interference. And if you work that out with the same small angle approximation, you're going to get x min, in this case, is 0.15 meters, right? That's because we have that extra half wavelength, that's where our destructive interference point is at. And it actually wasn't scored, but it is important to note that you should be ranking this as 1, 2, 3, not right, not same though the points 1 and point at 0 x equals 0 and the point at x equals 0.3 are both maxima. They're not the same, right? This would be right. That would be saying the same. That's not right. But they didn't actually score that. You just had to recognize that this was the brightest and that was the dimmest. Right. Okay. So now we have some modifications to this setup. In part D, we decrease the wavelength by a factor of 3. So lambda goes to lambda over 3. So what happens to x max? Let's go here, right? We have this calculation. Our first maximum is given by that formula. So if we divide lambda by 3, we're going to x max by 3. Right? Just to divide both by 3. Right? Just by 3. And so that will get us, right? So that means it'll be at 0.1 meters. But since this is a linear function, right? If you double lambda, you double x max, and so on. This means that we'll also have maxima plus or minus 0. And then the last one at 0.3. Okay, so now we can actually make the graph. We have to be a little bit more detailed because we have a little bit more going on, but it's not very different. Right, so we still have maxima at the center, but now we have maxima that are sort of subsequently decreasing at 0.1, 0.2, and 0.3. And this also means we have minima right at the center between each one, just like we did before. So our shape is going to be a lot sort of faster oscillating of the sine curve. Right, it will look kind of like that, roughly speaking. And again, it doesn't have to be perfect, it just has to be curved, and you have to have the minimum and the maximum in the right places. The key is to show that you know where those maxima should be. That's a calculation that you can do. And then similarly, you should also be showing that the maxima decreases as you go out from the center. You probably want to exaggerate it actually a little bit more than I did in this drawing, but this would be fun. And then finally, in part E, we're changing from a single slit to a double slit. We keep the wavelength at its 0.8 times 10 to the negative second meter value, and we have to figure out what the pattern looks like. And this is something that the equations you can kind of mislead you on, because you only have that one equation. We have to figure out how to apply it to the double slit. And remember, for a double slit, we use half the slit size in place of the slit separation. So the equation is really more like this. Right, for a maximum. Or for a minimum, right, something like that. Right? And the minimum is useful for this because we can just get rid of the decimals or fractions and cancel it out. We can still use the small angle approximation. So this is going to be more like AX min over L equals M lambda. So we can solve for where the first minimum, M equals 1, is. We get X min is lambda L over A. And you notice that this is what we found for the max of double slits, right? And so that means that it's going to look kind of like this one up here, because our wavelength is the same. But wherever there's a maximum in that one, there's going to be a minimum, right? So what will that look like? Oh, and I guess I should also say, and vice versa, right? Places where there's a minimum, there will be a maximum. I apparently cannot draw a very good straight line. Okay. 0, negative 0.3, and 0.3. Okay. So where do we put our maxima? We know the center is still a maximum. That doesn't change. That's always true. 0.1 has to be a minimum. 0.2 has to be a minimum. 0.3 has to be a minimum, right? All the places that were maxima are now minima. And then we have to put a maxima in between every minimum. And it has to be a decreasing one as well. Right? And it's symmetric. So it should look kind of like that. Right? And that's roughly it. Again, the key is to show the calculation that you can relate sort of the one equation that we're given to the single slit rules, which are slightly different than the double slit rules. And from that, make the plot accurately with the sort of decreasing maxima, and so on. And that's that.